Now, the authors then does an example, and you need to understand that in this specific example, this magnitude of 20 decibels is specific to the example. It's not generally so that you want to drop 20 decibels, but in this example, the idea was to drop 20 decibels. So what it shows is that the uncompensated Bow diagram of this closed loop system, uncompensated loop transfer function Bow diagram is given by the black line in magnitude at the top with the scale on the left, and the black line in the bottom is the phase of the uncompensated loop transfer function with its scale on the right-hand side. And as you can see that this magnitude curve drops through 0 decibels here at the frequency of, looks like 6.5 radians per second. And at that frequency, the phase curve is merely 20 degrees above the critical minus 180 degree line. So the phase margin is merely 20 degrees. And in this case, they were targeting a phase margin of 45 degrees. So note, unlike in the case of the lead compensator, in the case of the lead compensator, we would have worked with the difference between what we want, 45, and what we have, 20. In this case, we just work with what we want, the 45 degrees. We add 5 degrees to that to account for the reduction in phase caused by the compensator 1 decade away from the 0. And then we ask the question, at what frequency will my phase margin be then 50 degrees of my, if I look at my, just the phase curve of the uncompensated system. And so from that, I then determine, first of all, according to the procedure, my frequency omega sub c accent. So this is the frequency where I would like my magnitude curve to drop through 0 decibels. Because if it does, I will have perhaps not 50 degrees, but at least 45 degrees, because I'll sacrifice 5 degrees by having the 0 1 decade below my omega sub c. Now, of course, the moment I've determined omega sub c, I immediately can place my 0 1 decade below this. So if you see here, my omega sub c accent is something like, let's say, 18 radians per second. Sorry, not 18, 1.8 radians per second, just below 2, which means that my 0 position sits at 0.18 radians per second. And then I need to determine my alpha. My alpha would be such that 20 log alpha is the amount by which my magnitude curve needs to drop to go through 0 decibels right here at this frequency. And in this case, it's 20 decibels. But in another case, it may be a different number of decibels. Point being that this 20 decibels, this amount of magnitude in decibels can be converted to calculate alpha. And the moment you've calculated alpha, that determines the position of the pole at lower frequencies. And now my design is complete because this is my pole, that is my 0. Note that both the pole and the 0 sits at very low frequencies, very far away. And this is important because one could have argued before one fully understood the theory that it would be crazy to use something like a lag compensator, because as we can see in this curve, the lag compensator reduces the phase, and we don't want to reduce the phase because reducing the phase in general is destabilizing. We would like to increase the phase of the loop transfer function. As a general statement, we want to increase the phase to make the system more stable, to increase the phase margin. And therefore, one would almost say nobody in his right mind will use a lag compensator because the lag compensator will reduce the phase. It is destabilizing. Now, the point is this. Yes, we do actually reduce the phase, but we reduce the phase here in the low frequency range where it does not matter that we reduce the phase. In the critical frequency range where it does matter, in the range where the crossovers happen, there the phase is back to what it was. And here we, in other words, do not have the negative effect of dropping the phase that is associated with a lag compensator. The phase is dropped only at low frequencies. But in order to have that, both the pole and the 0 should be sitting at low frequency. So that is why we can conclude, and the authors mentions this in the text also, that your lead compensator pole and 0 normally are at relatively high frequencies, where in the case of the lag compensator, the pole and zero are at relatively low frequencies. And here then you can see that even though we haven't really, in the region of the crossovers, changed the phase curve in any way, we have actually changed the phase margin by causing the magnitude curve to drop through 0 decibels at a lower frequency. Note though that if I look at specifically what is going on here, below the pole, at low frequencies, I don't want to write anything now. At low frequencies, the loop transfer function magnitude is not changed, which is because of the fact that the DC gain of my lag compensator is 1, and therefore it means that the steady state error requirement, if I've worked correctly, will still be met. Well, if I see it on the graph that at low frequencies the two curves fall on top of one another, that is a sure way of saying that I still meet the steady state error requirement. It is, however, a good idea to just check it at the end of the procedure. Figure 1019b shows the general effect in terms of step response of a lag compensator. The uncompensated closed loop system would have a response indicated by the black solid line, high overshoot, very oscillatory. But after we've inserted the lag compensator, the overshoot is reduced, the oscillation is reduced, but you can see that the system is quite a bit slower. It slowed down the response. My last slide, I'd like to point out just two errors in this figure, figure 1017. First of all, this shows a root locus diagram with where the loop transfer function has got a pole at -2. And if you apply the rules of root locus diagram, you'll confirm that the real axis to the right of -2 does in fact lie on the root locus diagram. But that means, since this is a single pole at -2, that there cannot be root locus diagram located to the left. So this is wrong. That shouldn't be blue. It should be a black line. And then secondly, the second error is that the circle, two branches that's encircling the 0 at -z, they should both, to have this, the root locus diagram symmetric about the real axis, this arrow direction is wrong. It should also be like this, as I'm indicating it here. In other words, the loop that goes at the top goes anti-clockwise, the one at the bottom goes clockwise. Because the two branches starts at the two loop poles, move towards one another until the breakaway point, and then break away upwards and downwards until they break in at this point, and then one branch goes to the 0, and the other one goes to the left until it meets the second breakaway point. Okay, so that then concludes this recording.